So we'll take a second and I want to do some examples with you guys here. So let's take a look at this. What if we have a molecule that has only C's and H's with Mz M plus equal to 100? Well, with that, we just have to make guesses. So you might guess 7 carbons. So 7 carbons is a molar mass of 84. That'd give you 16 H's. Right? You get 16 because 100 minus 84 is 16. So C7H16, good starting point. Doesn't mean it's correct, it's just a good place to start. All right, what if we had this? What if we had an M plus equal to 110 with the index of hydrogen deficiency equal to 2? And again here we'll say only C's and H's present. All right, well, you might guess 9 carbons. 9 carbons is 108, so that's not going to work because that would give you a C9H2. Unlikely, right? Not a good guess. So then we'll come down here and we'll guess 8 carbons. Right? 8 carbons here is equal to 96. So for H's, that would be 110 minus 96, which is 14. 14 H's. Well, so that would be a C8H14. That sounds reasonable, but is our index equal to 2 for that? So the index would be 2 times 8 plus 2. That's where your H saturated. Minus 14 divided by 2. So that's 16, 17, 18. 18 minus 14 divided by 2. 2. Looking pretty good there. Again, that doesn't mean that that's our actual molecular formula, but it's a good starting place though. All right, let's do another one here. So let's say that we have here carbon, nitrogen, and hydrogen with an M plus equal to 112. So even molar mass equals even number of nitrogens. So I'll start off just guessing that we have 2 nitrogens here. That gives us a contribution of 28. All right, so 28, well, let's see. 112 minus 28 is equal to 84. So then maybe the rest is due to carbons and hydrogens. So with that piece of information here, we then come down and we're going to say, well, what about 6 carbons? That gives us 72. 84 minus 72, 12. That gives you 12 H's, which is 12. That adds up to 112. So then we might guess C6H12N2 for our molecular formula. Let's do another one. There's one other kind of pattern that I want to show you guys here. So sometimes M plus 1 data is given to you. So if your M plus here for this example is equal to 86, and your M plus 1 mass charge is 80, it'd be 87, right? It's one more. But let's say that these abundances were given to you, and that the abundance of your M plus was 20.9%, and the abundance of M plus 1 is 1.20%. So there's a nifty little kind of relationship that we can use here to help steer us in the right direction. So if we take our M plus 1 and we divide it by our M here, and then we multiply by 100%. So M plus 1 we said was 1.20%. M was 20.9%, right, times 100%. That equals roughly 5.74. Okay, so now if we take that number, and it's a percent, by the way, so if we take that 5.74% and we divide it by 1.1%, why are we doing 1.1? Well, this is the natural abundance of carbon-13. So if you do that, you get 5.21, and that's essentially our number of carbon atoms. You can see it's not perfect here, so you don't have 5 1/5 carbons. You're probably going to guess 5. So guess 5 carbons here. So 5 carbons is equal to 60. Okay, so then we take that, and our molar mass was 86. So 86 minus 60 equals 26. Right, so a C5H26, not a good guess. So there must be something else present here. So we only have 26 to play with. It's an even molar mass. So we could have an even number of nitrogens, but that would give us 28. So that doesn't work for us because 2 nitrogens would contribute 28. What about oxygen? So if we remove, for this, 16 for an oxygen, that would be 26 minus 16 gives us 10 H's. Well, that seems good. So 5 carbons, 1 oxygen, and 10 H's. So then putting all of that together, C5H10O would be our gas. Now then we go, and this is what we're going to do, we're going to go take a look at IR, we're going to look at proton NMR, we'll look at carbon-13 NMR, and then we'll be able to deduce the structure. It's like a puzzle.